Maths. Course schedule. I don't know the question. Given an array of such represents the index I is equals to A and B. It is a mistake course B if you want to take course A. Here's your analysis mistake course 1 for A course 0. The lab norm courses you are required to take label from 0 to the last. Return to if it's possible to finish all courses, otherwise return course. Non-courses equals to from 0 to non-course, so 0 to 1. Yeah, 1, 0, 1. Yeah. First take part 1, compare difference, then take was 0. Non-course equals 2, course is equal 0, 1, and 1, 0. In order to take course 1, in order to take in order to take course 1, you need to take course 0, then to take course 0, you must take course 1. Bruh! What? Oh, where B will always be the first. So in order to take course 1, you have to finish course 0 and finish the B. You have to finish A. I don't know how solution, bro. Cycle direction VFS. Oh, cadence and cons algorithm. Oh, wow. I don't know what the heck this is.
Hey everyone, welcome back, and let's write some more neat code today. So today let's look at a graph problem actually. It's called course schedule. We're given a total number of courses, and these are our nodes, and they're labeled from 0 to n-1 basically. So some courses have prerequisites. For example, if you want to take course 0, you have to first take course 1, and that's represented as a pair or as an edge in our graph. So if you want to take course 0, you have to first take course 1. And the only question we want to answer is it possible for us to finish every course? So let's just look at the first example. We're given number of courses are 2, so that means we have one course 0 and another course 1. We know that the prerequisites are like this, meaning that if we want to take course 1, we have to first take course 0, and I'm going to represent it as an edge going outward from 1 into 0. So what do they mean by possible? Let's just run through each of our courses and see, is it possible to take each one? So for 0, is it possible to take 0? Well, we don't have any outward edges from 0, so that means 0 does not have any prerequisites. So it is possible for us to complete course 0. Then we look at course 1. It has one prerequisite, which is 0. And we know 0 is possible to complete, so once we finish course 0, then we're allowed to take course 1, which has no other prerequisites, right? The only prerequisite was course 0. So therefore, both of these courses are possible to complete, so we can return true. So let's look at an example where it's actually impossible. So we're given n equals 2. That means we have two courses, 0 and 1, and we're given two prerequisites, so 1, 0 and 0, 1. This one means that if we want to finish course 1, we have to first complete course 0. So 0 is a prerequisite. The second one means that if we want to finish course 0, we have to finish course 1 first. So 1 is a prerequisite of 0. So the problem with this is kind of obvious, right? There's a cycle. So if we want to finish course 0, we got to go finish course 1. If we want to finish course 1, we got to finish course 0, and it just goes like that forever. So neither of the courses are possible to finish. So in this case, we return false. So we can actually solve this problem using depth first search. We can also use breadth first search, and I'm going to show you just the depth first search version because I like it better. So given this new example, the first thing you want to do is visualize it. So I'm going to draw a picture. So we're given 5 nodes. So we have 0, 1, 2, 3, 4. That's 5 nodes. We're also given 5 prerequisites. So in this case, we end up having 5 edges, right? From 0 to 1, 0 to 2, 1 to 3, 1 to 4, and 3 to 4. So my goal here is for each of these nodes, I just want to know, right, for each of these classes, can we complete this course or not? And how do we know if a course can be completed? Well, just looking at this picture, it's obvious, right? 0 has a prerequisite of 2, but 2 does not have any prerequisites, which is great. It also has a prerequisite of 1, and 1 has 2 prerequisites, 3 and 4. 3 has 1 prerequisite of 4, and 4, luckily for us, does not have any prerequisites. So looking at this, it's kind of obvious that we can complete all these courses. So let's do the algorithm to be able to determine that. We see that these are kind of our base cases, right? 2 and 4 don't have any prerequisites. That's useful information, but we don't need a graph to tell us that. We can use a data structure called an adjacency list, and I'm going to call it prerequisite map because the data structure I'm going to use is a hash map to represent this. So for each of our courses, we are going to have a list of all of its prerequisites. So for 0, we know 0 has 2 prerequisites, 1 and 2. And we're going to repeat that for every single course. So for 1, we know that 2 does not have any prerequisites, so we can just put an empty list over here. 4 also does not have any prerequisites, so we get another empty list. So now we're going to run depth first search on every single node. I'm going to do it in the order from 0 to n minus 1. So be starting at 0, so we're going to run depth first search on it, right? How are we going to do the depth first search? Well, we have our prerequisite map, so we're going to do it recursively. We see that it has 2 prerequisites, 1 and 2. So now let's run depth first search on the first neighbor 1. So now we look at 1, we see that it has 2 neighbors, 3 and 4. So let's recursively run depth first search on its first neighbor, 3. So since 3 is a prerequisite of 1, now we want to know if we can complete course 3. So we look at its prerequisites. It only has 1, 4. So now we're going to check its only prerequisite 4. Can we complete course 4? And then we want to look at the prerequisites of course 4, which we know are empty. This is good, right? So now we see that this is empty. So what does that tell us? That tells us course 4 can be completed, which we basically already knew because course 4 has an empty prerequisite list. So I'm just going to put a little check mark here to say that we know course 4 can be completed. And so recursively, we're going to end up going back to our 3, and we see that it only had 1 prerequisite, and we were able to complete that prerequisite 4. So therefore, 3 is also a course that can be completed. And so what we can actually do is from its prerequisite list, we see 4, we can just remove the 4. We know it can be completed. And so I'm representing that by having an empty list here, right? Just an empty list means that it has no prerequisites, therefore it can be completed. So I removed the only prerequisite that 3 had. Then from 3, we can actually go backwards to 1, which we see here. We can kind of get rid of this 3 because we know 3 can be completed. And then from the 3, we're going to end up going to 4 to check again if 4 can be completed because it is a prerequisite of 1. And since we already know 4 can be completed, we can get rid of that as well. So now we know for sure that 1 can also be completed. And now I'm going to go back to 0, which is how we even got to 1 in the 2. So now it has no neighbors. It has no prerequisites. So I can put a little check mark here. 2 can be completed. And then we can finally go back to our original node, 0, cross out. Notice in this graph, we have to visit every single node, and what we're going to do, we can instantly do that. We don't have to go through its prerequisites twice. So I'm going to show you one last example. This is the example that what we're going to do, how are we actually going to detect this loop? Because we see, so I'm just going to cross this stuff out because we're looking at a different example. But here we see that 0 has a prerequisite of 1, 1 has a prereq of 2, 2 has a prereq of 3. So this is a loop. We cannot complete these courses, but how can we actually detect this loop? I'm going to show you how really quickly. So to detect a loop, I'm going to use one last data structure, and it's going to be a set. Though I think you could just use an array if you want. I'm going to call it the visit set. And all it's going to contain is the list of courses that we're currently visiting along our depth first search. So let's say we start at 0, then we add 0 to our visit set. We take a look at the prerequisites of 0. We see it has 1 prerequisite. So then we move to 1. So now we visit 1. So we're going to add 1 to our visit set. And we look at the prerequisites of 1. It has 1 prerequisite 2. So then we move to 2. We run depth first search on 2. So to do that, we have to first visit 2. So 2 is also going to be added to our visit set. And lastly, we see 2 has 1 prerequisite of 0. In the we detected a loop. What I want to do is create our prerequisite pair from that list that I'm just of the prerequisites or pre-map. So our list of prerequisites. So we know for each course, initially we can set it to an empty list. So an empty list of prerequisites. And we want to do that for every course that we got, which the number of that is just number of courses. So this is, if you're not familiar, this is some Python stuff. I'm just saying that for every course, initially, we want to map it to an empty list. And we know that the prerequisites are actually contained in this nested list variable. So let's iterate through that. Let's get each course prerequisite pair from that list and then just start appending them. So pre-map of course, we want to append to this list this
Prime range of some courses is gonna keep making an array value for each integer for key value pair, and it's gonna be inside dash now.
prerequisite. So we also want a visit set, which is going them. So prerequisite pair from, let's iterate through that. Let's get each course prerequisite pair from that list and then just start appending them. So pre-map of course, we want to append to this list this prerequisite. So we also want a visit.
Okay. And for course, or prerequisite. What's up? Map for from the course of the sun.
Which the number of that is each. We want to store all the, we want to append to this list this prerequisite. So we also want a visit set to just start appending them. So pre-map of course, we want to append then just course prerequisite pair from that list and then just start appending them. So pre-map of course, we want to append to this list this prerequisite. So we also want a visit set, which is going to store all the courses along the current depth first search path. And of course, it's initially just going to be empty. So since we're going to do this recursively, I'm going to define a nested function, depth first search, inside of our can_finish function, because then we'll have access to all these variables without having to pass them in as a parameter. The only parameter that we have to pass in is the current course that we're visiting. And so like most recursive functions, we want to look at our base cases first. The first base case is if course is in the visit set already. So what this means is that we're visiting a course twice, so we detected a loop, so we can return false, meaning that this course cannot be completed. The other base case we know is if the prerequisites of this course happen to be an empty list. What that tells us is that this course has no prerequisites, and we can return true because it can definitely be completed. If neither of these conditions is satisfied, then we can take this course and add it to our visit set, because that means we are currently visiting this and we're going to recursively run depth first search on its prerequisites. So I'm going to loop through the prerequisites of this course. For each one, I'm going to first visit satisfied, then we can take this course and add it to our visit set, because that means we are currently visiting this and we're going to recursively run depth first search on its prerequisites. So I'm going to loop through the prerequisites of this course. For each one, I'm going to run depth first search on it. So depth first search on this prerequisite. If it happens to return false though, then we know we can return false immediately. We don't have to wait, because if we find one course that can't be completed, then we can return false for the entire function. So I forgot to put a not over here. So if not, meaning if it returns false, then we return false. But if this does not execute, that means it's a course that can be taken and we want to return true in that case. But before we return true, we want to remove it from our visit set, because we are no longer visiting this. We've already finished visiting it. So visit, remove this course. And also, since we know this course can be visited, what we can do is say pre-map. We can set it to an empty list, so that if we ever, we can set it to an empty list, so that if we ever have to run depth first search on it again, we will in that case execute this condition and return true immediately. We will not have to repeat all this work of running depth first search on its neighbors. So that's all for our depth first search function. The function is done. All we have to do is call it now, but we have to potentially call it for every single course in the number of courses that we have. And if any of them happen to return false, then we have to return false immediately. And if they don't return false, then we can return true. All courses can be completed. And the reason we are looping like this is mainly because what if our graph is not fully connected? Like, what if we have a graph like this? One has a prerequisite of 2, and maybe 3 has a prerequisite of 4. So these are two separate graphs that are not connected, right? So we have to manually iterate through every course and check, can 1 be completed, can 2 be completed, can 3, and can 4 be completed. So this is the depth first search solution. You can see that it does run very efficiently.
I did not understand. Okay, good night.